So I want to try to give us a slightly different kind of talk, where a little bit more, a bit of an overview of many things. So, but the idea is still always to try to understand human movement. How do humans accomplish incredibly skilled things like a ballet dancer, like this one? How can we understand it in a constructive way? So obviously this is a question that is so important that lots of people, in fact whole faculties and departments have been looking at it. So I want to try to highlight some aspects of this problem that I think make sense to have people in computer science try to look at it, or people from the kind of backgrounds that most of the people in this room have. And this is also an overview of the rest of the talk. So I'm going to first very briefly introduce some of the complexity in modeling human movement. And this is going to be actually very brief. Most of the time I'm going to spend on talking about how do we simulate the dynamics of human movement realistically in the computer. So this is going to be the bulk of the talk, mostly things that you would recognize. Then I'm going to spend a little bit of time towards the end on some newer things. I should say some of this I'm talking about for the first time, so you're hearing it first. So I want to talk about how to model muscles at the physiological level themselves, and I'll tell you why this is important. And finally, I'll talk about neural control. How does your brain control movement to actually produce the kind of skilled motions that you would see? So the first thing to realize when looking at human movement is that it's a really complex machine. It is much more complex than any airplane or anything that you might have thought about. And even very simple everyday movements like reaching for this cookie involve all of these muscles pretty much all the time. So how these are coordinated is actually the central question, perhaps, of in neuroscience of motor control. So to be able to answer those kinds of questions, it is essential to actually have this complexity in your model. If you don't have it in the model, you may miss it. And this is a theme I'll come back to at the end. The second point that many of you may not realize is that there are all kinds of clever mechanisms in biology that we barely have begun to understand. You can look at the back of your own hand, for example, and when you move your fingers around, you'll of course see the major extensor tendons, but there are also all kinds of other connections there that we're not exactly sure what they do. But they seem to be, in some sense, messing up your inverse kinematics algorithm or something, making the picture more complex. Which is kind of funny, because most of the people in neuroscience believe that the brain is somehow trying to make things simple. So why are we making these things more complex? In fact, if you open up your finger, you can't see this, but you'll find what looks like some very complicated machine that people have known for basically since the beginning of anatomical studies of Vesalius and Da Vinci. But we still don't have a good idea what it does. So we want to be able to represent these and model these kinds of complexities. And by the way, these have real consequences. One is this type of deformity you could have if one of the tendons becomes slack. I experienced one the other day when I was trying to finish a grant proposal, when people who use Emacs, for example, are likely to get inflammations in one particular lateral band in there. So this is actually very relevant to computer science, especially Emacs users. But people have, when I've mentioned this, people say maybe this is really the hand, the crowning achievement of of human evolution, perhaps. But what about the eye? Maybe the human eye looks very simple. It has just 3 degrees of rotational freedom, perhaps. So what about the eye? Maybe it's much more simple. And in fact, actually, it has been discovered relatively recently about, by one of my collaborators, Joel Miller, that in fact there seems to be some things holding the eye in the orbit. Some very complicated looking mechanisms like this. This is a reconstruction from histology data by Joe Deemer at UCLA. But even the simple eye underlying it has some complicated mechanical structure that is driving it. So we want to be able to understand and perhaps exploit the ideas behind these types of things. So by way of background, the main point is that we can't sweep all these complexities under the rug. We have to represent them explicitly to understand what the brain does. Okay. So how do we do this? So the thing you do is, of course, build biomechanical models, and this is an area which has also been studied extensively. So let's look at some aspects of simulating this realistic dynamics. So the first question is the most basic one you can think about, which is dynamics involves moving mass, and how do you represent the mass of muscles in your body? It looks like the most elementary question you can possibly ask about simulating human dynamics. So if you look at most of the work, I mean essentially all, in how this is done, most of the simulators basically build the dynamic algorithm on top of algorithms that were developed for robots. They're initiated in robot simulation, and then they added muscle-like things on top of it. Okay? So how do you account for muscles then in this framework? Well, one thing you could do is you could take all the muscles, say, in the upper arm, lump it together and say this is a rigid body like this. This is my upper arm. This is the lower arm, the segments of the hand, etc. This is basically what everybody does. And it seems like a reasonable thing to do, that it looks like a segment like that. Right? So what's wrong with this picture? Well, before looking at that, let's see, maybe as computer scientists don't know how to do this, but in fact, if you look at all of these papers, as an example in biomechanics, famous software packages like, for example, OpenSim is a large effort out of Stanford funded by NIH to build a biomechanical simulator. UBC's own ArtistSynth, which actually does a lot of things, but I think the muscle dynamics uses this type of a model. So basically, almost all current models use. So what's wrong with this picture? So let me just give you try to do this little demo. Let me see. I think I have a toy. I have this toy right here. So this is a piece of mass, right? Just like it's a car, and if I can look at how it slides down the slope. Okay. So this is I could build a model for it. I could simulate it. So now I put the car back. What happened? It suddenly stopped. It's suddenly much more sluggish. What did I do? What did I change? Well, effectively, I turned it around, but effectively, I put it in gear. Okay, so the only thing that changed is the gearing in there. And what that meant is that in this configuration for the car to go down the hill, it has to spin this big flywheel around. It has to move the mass internally. So the same kind of phenomenon occurs when you move your arm too. When I move my arm like this, up and down, holding my upper arm fixed, the only mass that is moving is not the mass of the distal limb. The muscles that move this are not physically moving in this direction, but they're internally moving up and down. So you have to move all of this mass. That means that they play a role in the inertia. So you could build you could analyze this. I built like the simplest possible model of this so that people could work it out on pencil and paper to convince themselves. So you can take like a 2-link arm like this with one muscle, and with this muscle you can do the kind of things which would be a homework assignment in my course or robotics or computer animation courses. You could compute for a point of mass on the muscle what its velocity would be as the joint angles of this arm change. You can write down the kinetic energy, inertia, etc., and you end up with some matrix which is the inertia of this arm as viewed in joint space. For people in robotics, etc., this is a very familiar type of a concept. It's just a generalization of what mass is to a configuration space. So you can look at the errors and you find that the errors can be actually complicated and large. In fact, it has some cross-coupling, which makes it hard to just eliminate it easily. There's even kind of a lower bound, which doesn't go away in any posture, so it's a good, gives you a sense of what it is. Basically, the error you make is the mass of the muscle time divided by 3 times something like this leverage that it gets at this point. So it can be large. For example, to make it concrete, I simulated a simple leg-like thing with one muscle, of course not a real leg, but with the similar masses. If you drop it to the ground like this, so what happens? Let's see. So within about 300 milliseconds, when the leg hits the ground, you already make errors of about 3 centimeters. And this shows that basically making errors in inertia because they affect the acceleration that gets integrated all over time, can actually accumulate and can be significant. And there's the code and as well as lots of other examples in the paper. So, but the point I actually want to make is that it's not just that, we found a correction to the error, but I think it's actually a fundamental principle. This is actually, I put this picture up partly because how is it possible for somebody like this to land on a toe and not have the toe fly around? Or for that matter, if you play keyboards, how is it that you have a tiny little distal phalanx coming and having a large impact with the environment? Why doesn't it fly around? One reason is that the inertia of the joint is not just that due to the little bone there. It's due to the bigger muscles that are connected to it. So you have to take that into account. So our solution, this is actually in some ways back to the future because we've been simulating this before I did that analysis. I've been saying this in my introductions and people didn't believe me that it was important for us, so I just did a small example there. So our solution has been to use these things called strand models, which are abstractions of thin solids. Initially introduced for simulating things like sutures, but Shin Sueda, as part of his PhD work, really took it to the next level and built a really nice dynamic simulator for biomechanics, which basically builds on top of that. The main difference is now these muscles actually have some physicality. They have inertia, they have other distributed properties. Here's like an example, just to show that you can simulate like a whole arm relatively efficiently using these type of strand-based models. I'll briefly go over how it works, just to give you a flavor, and not so just to see what's under the hood. But this is all in the papers. So the idea is that you have rigid bodies, just like in any multi-body dynamic simulator. But in addition, you have these things called strands, which are parametric curves of mass that you can then discretize and simulate, and material properties that vary along the length of the strand. So it's a physical object. So here's just an example showing that you can dangle it, and it feels like a thin solid and not like just a curve. So you can derive the dynamics of this object, and you can then simulate the whole system of strands and rigid bodies together. So your system's configuration space includes that of the rigid bodies in there, as well as all these strand-like objects. You put them all together, and then you can simulate it. Except that one thing that I've left out is the fact that you need all these constraints holding these strands together. This is, of course, just an extreme case to show what happens if you take them out. But the point, which I will also come back to a little bit, is in some sense constraints are more important almost than dynamics. And dealing with them well is an important part of simulating these kinds of things. So in this particular version of it, we basically have things like, of course, the joints between in the skeleton, but also constraints between the strands and the rigid bodies, and some things like sliding on surfaces and also through constraints. So remember that finger-like example that I showed you, what the complexity of the mechanism inside the finger is. Well, you can simulate those kinds of things with these constraints. So we put these together just for the technically interested people among you. This is, as the people like Uri know, it's like a high-index differential algebraic equation. So, but we solve this in a way that seems to be something that's actually has many reasons why this is an optimal way to do it, which is that you solve for these constraints at the velocity level first, and then you integrate them and get them at the position level. At the velocity level, it leads to this type of KKT matrix, which again, about those of you who've seen it have seen them all your life. These occur everywhere when you have some kind of optimization with constraints. These are large, sparse systems that you can solve efficiently, and then you can simulate your finger. Just to parse this a little bit, so here is the strands are, first of all, connected up. You can build a network of them with these cyan dots. You can connect them up. You can also constrain them to slide in tendon sheets and things like that. Those are the green dots, and these purple dots represent constraints where the strand slides on top of a general, in this case, a B-spline surface. So you can see you can put in all of these types of this type of realistic complexity into the model, and you could simulate the dynamics of a finger. This is, I think, of interest to not just biomechanics, but computer graphics as well. For example, this you can, by simulating the underlying structures, I don't know if you can see this with the lighting, but you can generate very realistic subsurface movement of skin. In terms of health, there are also important applications because it turns out that this kind of tendon networks have functional value. For example, when I extend my wrist, I automatically seem to close my fingers. Okay, this is something that you might, if you're not aware of biomechanics, you think, oh, that's a synergy, that's some kind of a coordination pattern that the brain is imposing on movement, but it's not. It's just purely in this mechanical structure there that, and it's useful if you have, for example, a partial spinal cord injury, which has paralyzed the muscles with which you can do a pinch grasp, but you still have intact the muscles that you can extend and flex the wrist. So you can get some pinching effect by just extending your wrist. So this has some medical utility as well. So I mentioned the eye in the beginning, just to also illustrate that very complicated network. People are beginning to realize, especially in aging, starts to deteriorate. And some people believe that this might actually cause some of the vision problems that people have as they age. Here is an example of a particular band deteriorating, and this, I don't know if you can see it with the lighting. But this woman, when she looks up, her left eye is not able to go as high up. It's called hypertropia. You can simulate these kinds of things. So you could turn this type of medical wisdom of how you diagnose various diseases, etc., into something that you can ask a computational model. You can simulate the sag in one of the bands, and then you could see what kind of movement it produces. Once you have a forward model, you can invert it to do diagnosis, for example, to see what could be the problem. So by the way, just as an aside, we are also trying to build we have built a robotic model, which is also tendon-driven like this. In the interest of time, I won't show you the video, but if you're interested, I can show you later. This is with Tony Hodgson in mechanical engineering and a co-supervised student, Makame. So once you have these biomechanical models, you can also build subject-specific models. Everything I've talked about so far has been what you could think of as normative models. This is how things should be. But as you know, some people look like Will and some people look like David Kay. They are scaled differently. So you need to build subject-specific models if you're going to say something to help, say, Will. So we've been looking a little bit into this about how do we fit these biomechanical models to imaging data from individual subjects. The preferred modality is MRI because it's relatively safe and widely available. We've also been looking at measuring the activity of muscles using MRI data plus a high-density grid of electrodes that you would put on your arm. This is with Uri Asher and Kees van den Doel. As I said before, you could also use these kind of models to diagnose impairments, and this is something that I've been doing with John Steeves and a shared postdoc, Jose Zarifa. I don't have time to go into all of this. I'll just show you one example of how this kind of thing works, which is that you, so the problem with MRI is that the images have very poor contrast between nearby muscles. So in any particular segment, if you treat this as an image processing problem, you can barely see where the boundary between one muscle and another is, but that contrast may be there somewhere else in the limb. So if you have a full biomechanical model template, then you can transform this whole model template into the image to build a subject-specific model. So Benjamin Gilles, who was a postdoc, is now a CR2 at CNRS in France, is the one who did a lot of the imaging work for this. So we can basically, this is showing just one muscle here, but I think you might have missed the beginning. Let me show you again. So how you can take a template, which is just a nominal model of what the muscles are, and you can fit it to an individual subject. Before leaving this topic of how do you simulate realistic dynamics, I want to share a couple of insights from recent papers at SIGGRAPH this year. Of course, it has a lot of nice videos. This is what SIGGRAPH requires of us. But there's a kind of, I think, a key numerical modeling insight underlying both of these papers that would be useful to take away, which is that when you try to simulate constrained objects, you have this problem of you have a discretization of the object that you are simulating, and you have a discretization of the constraint itself. And they don't often play well together. And this is really the underlying problem that I think we solved in these papers. So, for example, the actual tendons don't just go through point constraints, but they go through sort of long tube-like things where they are highly constrained throughout. So if you had a strand that was discretized in some way, it's going to get stuck inside. The discrete version of it is going to get stuck inside that tube. And this also occurs in other kind of places, basically, you know, wrapping a rope around something or going around a sharp corner. This looks fine, except when you realize both these things are known only to some discretization. So you want to make them somehow match. So in one paper, which was led by Shin, so it introduced two ideas. One is, of course, in some ways a more natural one, which is if you have lots of constraints, you could use reduced coordinates to represent just the degrees of freedom inside that constraint. The second one is not so obvious, and that is that you have to take a step back and realize that most of the time when we simulate solids, we use what is called a Lagrangian discretization. And that is, we actually discretize little bits of mass, and we track how these little bits of mass move around in space. So this picture there, which you just saw, let me just, is a cartoon of a Lagrangian discretization. The alternative, which has been used primarily in the fluids community, is called Eulerian discretization, where you discretize the space itself, and then you see what goes by. So you're sitting on the sidewalk, seeing what are the cars going by, and you're trying to say something about the solid. So if we put this thing in there, it has a lot of advantages. Maybe this is a table showing that we can match and mix all of these different, you can have reduced coordinates, and also you can have two types of Eulerian Lagrangian one. But if you look at this example here, this shows that, to simulate, this is like a little bead, let's say, going on this wire. If you have an Eulerian node there, so on the solid, you just need one node to watch what's going on, and you don't have to worry about a discretization of this this curve clunking through the solid. And so this allows, for example, to simulate complex machinery. We didn't do a biomechanical example just to be different. We did like something which actually I think is very. These old machines are very human-like. They have a power shaft like this, which is providing all the power in there. This is how factories used to work, by the way. You couldn't plug in the machine in the wall, but you plugged it through some cables into a shaft that was maybe connected to depending on how far you want to go, a windmill or something like that, which is providing the power. So this is driving a robot like that, a compound pulley, elevator, some gears, so lots of degrees of freedom, and you can basically, this is just to show that you can robustly simulate something with lots of constraints. You can hold, jam that robot, and the whole line shaft would come to a halt. It's also very advantageous and has some other interesting advantages when you try to simulate solids using this type of an Eulerian discretization. And this is, by the way, led by Dave Levine. It's part of his PhD work. So again, when you simulate an Eulerian solid versus a Lagrangian one is the thing that you'd be most familiar with, say with a finite element model. You build a mesh and then you track where the nodes of the mesh are going. With an Eulerian model, you just have a discretization of the physical space and you try to see what goes by. So one consequence of this is that you don't have to maintain your mesh at all. So huge numbers of papers are written about how to repair, adaptively change the mesh when the mesh collapses due to contact, etc. You don't have to worry about that. You also can deal more straightforwardly with another big problem, which is when you have contact, it's not just figuring out how to simulate the deformation of the solid when it makes contact. The big problem is how do you detect the contact in the first place? In fact, most of these simulators spend more time detecting the contact than dealing with it. So figuring out how to take lots of these potential contact points and what samples are sufficient, etc. All of those problems go away if you can do the collision detection on the grid. This is kind of a volumetric test that is really, I think, brought to light by the work of one of our visitors, Francois Faure, to do that you can do volumetric collision detection in a very robust way in this fashion. So, and the third thing is, by having everything on the same uniform grid, I think leads to lots of simplifications and efficiencies. As you know, a lot of the work is not just in terms of how many flops are involved in a particular computation, but locality of data and movement of data on modern computers matters a lot more than those types of things. So by having a uniform grid that you can index relatively cheaply without doing any pointer following, etc., has a lot of benefits. So I'm just going to show you some videos. I urge you to take a look at Dave's and Shin's talks. Oops, let me just step back a little bit there. Because the SIGGRAPH talks are online, will be online soon for all the details. But so one of the points is that you can directly simulate volumetric data. You can take a CT scan or something and you can simulate the dynamics. Of course, the bear is a bit of a silly version of this. And also to show you that you can do very close contact between objects. This is highly deformable rabbits and dragons which live in SIGGRAPH to show you that we can crunch all of these things together and deal with the contact and the dynamics in a very, very robust way. Okay. Let me move on a little bit. Okay. So far, what we've talked about is that there are lots of complexities in simulating human dynamics, the dynamics of movement, and we can bring to bear the things that we know how to do well, which is to compute these types of dynamics efficiently, robustly, etc., to bear. So now we're all set. We can simulate the human body. We just have to go to our physiologist friends and ask them to tell us, so what is the constitutive model for muscle? I need the equations for muscle. I want to put it in my simulator, and then I'm all set. I have all the math and the physics worked out. I need the physiology. I want to know what is muscle like. And so you'd think that this is I was hoping, like most of us, that this is well understood, and you just have to go to a physiologist and ask them. But it turns out it's more complicated, and we've done some work recently on this. This is primarily, this is a collaboration with a group in northern Arizona. Kisa Nishikawa is the lead on this, and our part of it was to do the computational modeling and tell them what works and what doesn't work, so that they can refine the ideas so that it's, I think, a very nice collaboration with them. And so from our side, the main work that was done by Sang-Hoon Yo, who's a PhD student in our department. So how do muscles work? So this is one thing for which there must be lots of people who have looked at it, and indeed there are. Lots of, not just people, famous people have looked at it. Right? So it's a bit daunting to look at muscle at all. So what most biomechanics simulations use are what are called Hill-type models. This is a kind of the standard textbook model. A.V. Hill got the Nobel Prize for actually doing the measurements underneath this, underlying this kind of properties. But basically, a muscle, in some ways, is like a spring. It's like a very complicated spring. But you can think about doing an experiment where you can pull the muscle to different lengths and see what force it generates. So if the muscle is not active in the sense that there is no neuron is talking to it, so it's just a muscle. It's not dead. If it's dead, it does other things. It's a living muscle, but nobody's telling it what to do, right? So then, if you pull it like this, then it's passive. So you get a nice exponential spring-like behavior that looks like this. So then you can stimulate it. You can drive the neurons that tell it what to do. Usually you drive it to what's called tetanus, which is the maximum activation, and you produce. You measure the force at different lengths, and then this is what you get. By the way, this kind of experiment was done by Hill himself, and I should mention how this is done, because this is important. So you stretch the muscle passively to a particular length, and then you turn on the gas, and then it goes, you measure what force it produced, you measure that. And then you draw a graph like this. Okay, so you can also then do things like you can infer from this what is the contribution of the active part to the force, and this is a bit of an artist's impression, but this is what it looks like. So you can use this type of model. In fact, this is what all the ones that I mentioned in the first earlier, this is what they all use. But if you go and try to implement it, and we rediscovered it, I should say, naively by doing it ourselves in our strand simulators, if you just go and implement it, you realize, hey, this is unstable. And why? Because if you're at a particular, say, length here, and if you're getting a particular force, say you're balancing a weight against this force, and then if you stretch it a little bit, the force drops. It becomes weaker. So the more you stretch it, the weaker it becomes, and this kind of cascade. So it has to, you believe that it must just kind of keep going until it perhaps goes somewhere up there. So it could pop to that point. So we were actually quite shocked about this. In fact, there was a computational biomechanics meeting. I asked people, so how do you deal with this problem? And they said we've never encountered it. And then it occurred to me they hadn't encountered it because the typical model uses an extremely coarse discretization of muscle. It has only one segment, so it cannot collapse because it's just a single segment held between two things. But if you have more than one element in your muscle model, then you will have some segments collapsing and other segments expanding to deal with this. So anyway, we found that in fact some people, including A.V. Hill, have known about this for a long time, and this has been discussed for quite some time. But what exactly it means was again not quite clear. So then it turns out another thing that has been known for about 50 years is that muscles have something called residual force enhancement, which is that suppose you're at this length and you activate this muscle, and the cartoon version has said if I stretch it, do I go down here, or what force do I get? That is what would cause a problem if my force fell down. But actually, when you stretch an active muscle, it increases. So there's a fundamental non-commutativity between activation and stretching in the muscle that has been known for a while. Here's some data from a paper by Edman. And this thing, by the way, cannot be explained by the model I went through very quickly. I'll just come back to it, of how muscle works. So a very short description of how your muscle works. Should be interest to anybody because that's the majority of mass in your body. And this is how any muscle, including like your heart muscle or the flight muscle in insects, so it is a highly conserved design, works, which is that muscles are built off these basic units, which you see here. This is actually a half sarcomere. It's about 1 micron long. And your whole muscle is chaining a whole bunch of these things together and stacking them up to increase the force and the amount by which they can change. But this is the basic unit of muscle. It's called the sarcomere. And this is, there's a symmetric part on the other side. And it works by having a thin strand of something called a thin filament and a thick filament. These are proteins made of actin and myosin. And the standard model is that myosin here on this thin film, which you see here, grabs onto the actin and pulls, and that's how you get muscles contracting. Okay? So in this model, there is no room for a force enhancement. And this is the model, by the way, again, Andrew Huxley, after he won the Nobel Prize for how neurons transmit, worked on this basically the rest of his life. So this force enhancement basically is the thing that we were trying to explain. And a part of this is because there was an important player in muscle that wasn't known until very recently. In 1976, people discovered a protein called titin. And it wasn't it wasn't a protein that was hard to miss because it was too small. It was, it was too big. People didn't notice it. It's the largest known protein in your body. That's why it's called titin. It actually goes from one end of the half sarcomere all the way to the other end. And it has a segment here that is an exponential spring. In fact, it's a very, it's a spring that can lengthen to 10 times its length. So it seems to play a role in all this how this works, but you can't just put it in there because it's too compliant to explain various things. So Kisa Ishikawa had the idea that basically this titin is winding around the actin filaments, and in fact the winding is done by the cross bridges between myosin and actin. So the standard picture was that myosin just pulls on the actin filaments. So the hypothesis is that it's actually rotating it, and there's a lot of evidence to show that it does rotate it. The angle of the attachment, etc., is such. So we built a model for this. Sang-hoon did some very nice simulations. I won't go into the details, but the punchline is that the model, with all the things that after several iterations of this is how modeling goes, we've had to put some things in, take some things out, but it actually makes a pretty good prediction of this type of force enhancement. So the thing to just pay attention to is this is the same curve we had looked at before. This is the active force decreasing, and in stretch it increases. In this winding filament model, the same type of force enhancement is seen. And in fact, other things like the force enhancement is not uniform everywhere. There's a kind of a inverted U shape. We can reproduce that. So at this point, it's a hypothesis with a computational model. We are waiting for people to do experiments to see how it is. It's very hard to actually go. You might naively think that you could go and image this, but you have to keep in mind that the whole sarcomere is about a micron, and these are proteins. There are single proteins. You can't put them in even a light microscope or something like that. You have to use crystallography and other very indirect methods to figure out what they are. Okay, so in the remaining time, I'm actually, I guess, running out of time very fast. I think so. You aim for about 1 hour. Is there?
I think you have. Eric can say for sure, but I think we have until 5.
Yeah, I don't want to keep people from.
We have until 5.
Okay, I don't want to go. Maybe I'll. Okay, so I'll try to go very quickly about the one part, and then I'll try not to go till 5. I'll try to go till about 4:40 maybe. So far, we've talked about the mechanics, and so it would be nice if you could also get some insights about the neural control, how the brain actually controls all of these things. In some sense, this has been my main interest, and the biomechanics has been trying to set the stage so that we can do meaningful work on neural control. Because if you don't understand what machine the brain is controlling, then you're going to be totally off track by trying to just look at the neural data. So I want to touch on 2 things. One is basically an application in some sense to robotics, about how we can take lessons of how the brain controls movement and build better robots. And then the second is some ongoing work on trying to understand how the brain manages all of this complexity. So the first one is this master's thesis work of Martin Lesmana and Axel Lundgren, who was a visiting student in my lab, with my collaborator Per-Erik Forsen, who used to be a postdoc in LCI before, and now he's in Linköping. So the idea, just to go back to robotics and vision. Actually, I should make sure I'm not saying something wrong about the current LCI generation of robots. So there's a big problem about robot vision, which is that robots like to move, just like all animals like to move. Right? So, but movement is bad for vision, and here's like an illustration just to say, here you have a camera that is starting from rest and starting to move, and we ran a face detector. This is a Viola Jones face detector. It's like a standard thing that, and when you have a good clear image, you can find all kinds of things. You do great computer vision. Once things start to move, you start to lose faces, and then and very soon, and this is the kind of speed that you'd expect an active robot to go, you can't see anything. So most mobile robots basically stop and take a picture, process it. Is that still the kind of case? What about the Google car? The Google car, Sebastian's thing, as far as I could tell, it has no active eye movement. It has lasers and other kind of things. So, so there is a trick that biology has invented a long time ago. In fact, all mobile animals basically use this, which is to have eye movements. So even fish have them, pretty much all vertebrates, and you can argue insects also have eye movements, but they tend to move their whole bodies because they're so light. So you need to stabilize. The first thing you have to do if you're a robot with vision is to get a clear image. And as you can see there, without stabilization, you can't see anything. This is with our stabilization. I won't go over it again, but even though there was a little bit of off-plane rotation, that's because it's a planar robot, you could see what was happening. So we built this experimental device where we've had it's a planar setup. So you have a camera, and then you have an inertial sensor. And this is what humans and in fact all vertebrates have, which is in fact some insects have a version of it. That is, you have an inertial sensor. Ours is called a vestibular organ. It's behind our ears right here, and it can measure acceleration in 3 dimensions, and it can also measure translation and rotational accelerations, and some of those are actually integrated in the canals themselves to produce velocities. So this vestibular system has been a fundamental part of the vertebrate design, but somehow we don't have this vestibular ocular compensation in pretty much most robots these days. So we built a simple version of that where I won't go through the details of this, but I just want to mention that the cerebellum, which is a part of your brain that is near the back here, which has about half the neurons in your brain, is in fact is believed to have evolved first to deal with this type of vestibular compensation. We have a model of the cerebellum here, which basically computes a correction to a very simple, say, a rough model you might have of how to compensate for this. So the architecture is you have a very simple model here called B for brainstem, and that is corrected by learning a correction using the cerebellum. So the difference between this particular architecture and others that you might have seen, in fact, maybe that Michael was using, is typically the big problem is to learn the correction, you need an error signal, and the error that you would like to have is, what did I tell the actuator incorrectly? That's called a motor error. But the motor error is not easily available to you. What is available to you is what's called the sensory error, which is the difference between where I'm, in the case of the eye, where I'm looking and where I want it to look. So the sensory error is very easy to measure and from the sensors. So this particular one actually uses a recurrent architecture where it predicts what the sensors should be seeing and uses that and compares that with what it's sensing to learn the correction. So there are many other aspects to this I don't have time to go into. I just want to show you that so you can start it up with a very poor approximation to how to compensate. The motion is exactly the same, by the way, of the head, but what you're seeing here is initially there is a lot of retinal slip, there's a lot of blur, but hopefully, I'm not going to run it till convergence, but hopefully you see that as you are seeing it, it's stabilizing much better, and this is driven by the retinal error signal. This shows the same type of thing with just, but now to show that there's no cheating, the perturbations are just with the hand to show that you can see the image there that's being stabilized automatically. Okay. Oops. So to finish up, the last topic I wanted to mention is to try to understand now. So you have this very complex machine, and in fact, probably I've been convincing you that it's even more complex than you thought, and so it must be hopeless to try to control this machine. So how does the brain manage to control such an incredibly complex machine? So this is something, by the way, it's a very close collaboration with Andrea Davella's group in Rome. It's so close that we have weekly meetings on Skype, separated by 8 hours time difference or 9 hours. It's not a lot of fun, but the timing, but the meetings are a lot of fun. So the idea is to, it's got lots of names because it's a problem that people have been thinking about a lot. One name is the degree of freedom problem. That is, you want to do something like manipulate a joystick, let's say, but you have this huge, complex mechanical system with hundreds of muscles that you could use to do that. So, and you have some goals, and you know something about the state, but how do you pick what to do? How do you coordinate all of these muscles? A related question, which is subtly different, is how do you acquire these skills quickly? Because if you have a very high dimensional system to try to learn something, some new skill with, you would have a hard time. So if you had a low dimensional space, maybe then you could learn things faster. So this is an old idea. I forgot to put the names. This is Sherrington. This is Nikolai Bernstein. The main thing to see is that they both have mustaches. So this idea has been around for a very long time. That's true. That's true. So the idea is that there are these modules in the central nervous system. They might be called reflexes. Some people call them motor primitives, just like they're building blocks on which you could build movements. They're called, probably the most widely used is synergy, this term. So this is, for computer scientists, this is some kind of a basis from which you could, is there some useful basis from which you can quickly construct movements? So this has been like a folk theorem. Everybody believes it's true, and it's easy to see why, because you can do all kinds of behavioral measurements, and you see results like I asked people to pick up this glass, and I could fit all possible ways in which they did it with a six, all the variance was explained by 7 basis functions. So it's 7-dimensional space, something like that. So this is it's based on regularities in the output. So there are lots of examples, but let me just show you. Oh, what happened to that one? So the kind of things that is done these days is you measure the actual, instead of measuring the movement kinematics, which might influence might have something of the arm dynamics built in, you measure the muscle activations using what's called electromyography or EMG. They're just electrodes you place on the surface, and you measure what the muscles are doing. So you could measure a lot of these things, and you could build a low-dimensional basis for it. So the big question is this modularity just in the data fitting? Is this just that you are able to approximate the data with the low-dimensional basis, or is it actually in the brain? Does your brain have a representation of this low-dimensional space in some fashion? And how do you actually test this? Is it possible at all to even try to answer this question? So we propose this a new approach to try to address this question by having a causal model. And it's based on the prediction that if you actually had a modular architecture, then there must be some things that are harder to do than if you used every degree of freedom that you had. So this is basically like a no free lunch theorem. That is, if you're going to put it in another terminology, if you're able to have a basis in which you get a sparse code for lots of the things that you see, there must be some signals for which you cannot have a sparse code with your basis. Right? So the tricky part is how do you make this thing possible? So the idea that we had is to build a virtual manipulation environment, and so this is actually, we have one of these here at UBC on the 7th floor and an identical one in Rome, and we run subjects on both the places. So the idea is that the subject sits and tries to manipulate some tools in this virtual environment, let's say like a single point object. But what is different is that as they are doing this task, we measure their EMGs, which are visualized. Maybe just stop it again. So you can see what muscles that they're using when they move. This is, by the way, an isometric task. The visual, it's like if you will, like a track point mouse. You push on it, and the cursor moves. So we now can build a myoelectric control model, which is now we can disconnect the actual forces that you're applying, and then drive the display purely using your muscle activations. Okay? So this is one step. So you learn a linear model which says, given a particular muscle's activity, what the force you would be applying on the knob are going to be. So okay, so now comes the tricky part. So what this allows us to do is, since we now can go directly from your muscle activity to a 3D display, we can then do surgery on your hand, which we wouldn't get ethics approval to actually do, not to mention you won't get volunteers. But we can do things like we can swap your tendons around. We could connect one muscle to something else. We could do whatever we want, because then we can show in the virtual environment what the effect of this surgery is going to be. So that's the basic idea. One more point to just clarify what this idea means is that, so what do muscle synergies? What is a synergy in this picture? Well, a synergy is if you are co-activating a whole bunch of muscles in a similar way in some low-dimensional basis. The basis is shown here. These are all muscles. So one synergy basically activates this one quite a bit and this one less, etc. So this is the basis. So you can extract the basis by also analyzing the data. And so this is what synergies look like. On the left is, again, the muscles that are activated. On the right is the effect on the knob of activating those synergies. So this synergy would move in this direction, etc. Okay? So is that picture clear? So your muscles, each muscle has an action at the end, and the synergies themselves, it's just a coordinated pattern of activating muscles. So they also produce some force at the end. Okay, so now this is the most important slide to try to understand, just to what we are doing. So the key point is that we could then do this surgery in two different ways. Okay? What you're seeing on the left here is the forces that would be produced by every individual muscle. Okay? And you can see it's an over-complete basis for 3 dimensions. So you can do anything you want with all of those muscles. Right? On this side is the basis of all the synergies. It's also complete for this space. So that means that by using these synergies, you could solve any reaching task in 3D. Right? So now the key is you can do the surgery in many ways. A simple way you can do the surgery is just rotate your muscles in this space. Okay? As you rotate the muscles, the synergies also rotate. What you see there is what's called a compatible synergy, in the sense that the synergy is rotated, but they are still a good basis for 3D, right? For positive combinations of these give you any point in 3D. Whereas you can do a dirty trick. You can rotate it in another way, in which the synergies now actually drop in rank. So that now you still have all of the muscles. We haven't changed anything about the actual, what your muscles can do. We only changed what the effect of the synergies are. So then you can check. If this synergy representation was actually in your brain, you must have a much harder time dealing with this kind of a surgery than if you had this one. Both will feel strange, but this one has the same synergies that you are using to perform the task are still good, they're just doing different things. Whereas here, you don't have it, none of those are not sufficient, so you have to recruit some new synergies or learn some new synergies, etc. So that's the key idea. So we can do that. So we can run subjects to do a very standard kind of center out reaching task. You have them do the compatible surgeries or incompatible surgeries, and then you can see. So the kind of data analysis for this is things that I can go over the results with you in detail if you like, but for people who are not used to looking at lots of graphs of data, it may not make a lot of sense. So I thought I'll just show you some actual trajectories from a subject. Right? So before, by the way, this is doing reaching with just your myoelectric control. So you're just using your muscles to reach. You do the surgeries, and suddenly you have a very hard time reaching. This is typical. This is the kind of thing that happens to people when they're getting recovering from stroke or other types of problems. So basically, they're going through rehabilitation now and trying to figure out what's happened to my motor system, because it's doing funny things. The first time they see this, they're going all over the place. The interesting thing is, after 8 blocks of this, you can see, at least qualitatively here, that if the perturbation was, if the surgery was compatible, you are getting back to a relatively good performance after this 8 sessions of, 8 blocks of training. Whereas in this incompatible case, still hasn't figured out how to reach that point. So it seems to be harder. There is another effect that people who do learning know. This is is there an after effect? Is there, when you suddenly take off the surgery, reconnect things up, if you learn something, there should be an after effect that you overcompensate, and you do see more of an after effect when you undo the surgery. So it looks like this is easier to compatible surgeries are actually easier, even though we corrected to make sure that because it's a rotation, it should be equally difficult tasks, the two, in terms of your muscles. To summarize this part, so it does look like it's harder to overcome, and I think that basically these results provide, I think, the first causal test and the positive. So it does look like there is these types of low-dimensional representations are in your central nervous system So I think that's a very exciting finding. So we are hoping to publish a nice paper on this soon. So by the way, in general, this type of myocontrol type of setup that we've developed, I think, is also an interesting way to do interfaces, for example, for all kinds of things. So I want to just conclude by, oops, I'm almost sort of going a bit long, but just very briefly what computer scientists, I think, can learn from playing in this area. It's, first of all, by the way, you don't need any other excuse. It's a very exciting area. It's really interesting. It's you. You're learning about yourself, how you work. But if you put on your hat as a narrow academic, you can still, I think, learn a lot from human physiology. So one thing is, I think, I've been making this claim for several places. I'm willing to take a bet if somebody wants to wager, but by 2020, I think the way to do computer animation is going to be to actually simulate humans and not just to make some tricks. I think Michael already showed some very nice results of how, by having controllers, you can generate not just a nice motion capture movement, but the things that generalize very well. We've also seen this happen in the physics area. Initially, people would do all kinds of dirty tricks to make physical effects like rain and cloth. Now they use things like Robert's simulations, which are simulating the actual fluids and the smoke and things like that to produce physical effects. But of course, nobody goes to a movie to see only the physical effects. What people go to the movies are to see the central human character, with all respect to Robert. No, but it is the case that what's the character, the human, is the central actor, if you will, and I think it's going to be the way to actually produce character animation. Human-centered design. I think for a lot of things, ranging from ergonomics of products to safety. My collaborator Mitsunori Tada in the Digital Human Research Center in Tokyo, they have all these projects to say, how do you know a cigarette lighter cannot be accidentally lit by a child? Well, you could recruit lots of children and have them try lots of designs, but if you had a computational model, you could let them at least pre-filter some of the designs to make sure that it's right. There's, I think, a lot of scope for biologically inspired technology. I think there are more amazing secrets in biology than are dreamt of in your philosophy. So I think you can. There's a lot of tricks you can learn to build better robots, to build low-powered devices, which is something that the biology seems to do really well. What about the other side of the coin? What can computer science contribute to human physiology? I think it's a lot. First, I could make a long list of all the techniques that we can contribute. The one high-level message about this, why this is important, is that scientists are constrained by their microscopes in some sense. If they cannot, if they feel that something cannot be done, they don't bother looking at it. Whereas by convincing people that you can simulate very large, complex biological systems, it's like a microscope, because it makes the scientists then try to ask questions that are relevant. Because if you say, I can only simulate a two-link robot, then the questions would be those related to two-link robots. But I think there's a more important basic thing. I was struggling with what to call it, that I think computer science can contribute. I thought of calling it culture, but I wasn't sure. But I think it's maybe, let me call it ideas. Ideas or culture. So I think computer scientists and engineers too bring some kind of a constructive bias. That is that you're not happy that you understand something if you just measure something and you can fit a graph to it. You want to build it. So unless you build it, you don't understand. You feel you don't understand it, it works. I think that is very important and valuable to prune a large number of potentially dead ends in this area. The other thing is, I think computer science, more than anybody else, has a lot of experience dealing with complexity, dealing with very large systems. So I want to kind of end by a couple of quotations to put this in perspective. One is by Sidney Brenner, who won a Nobel Prize in 2002, who said basically something like, the problem of biology is not to stand aghast at the complexity, but to conquer it. And he actually followed up to say that biology conquers it and finds all kinds of simple solutions like synergies, that type of simplifying assumptions. But the key point is, that's nice to say, but how? What is the simplification that still works? I think that is an important question that I think we can bring to it. I like this quote from Kristen Newgard, who actually gave a talk here shortly before his death about, for people who don't know, he's one of the fathers of object-oriented programming, and very passionate about actually teaching how you should teach object-oriented programming. And he liked to say that to understand object-oriented programming, one must look at sufficiently complex examples, not sufficiently simple ones. Because if you're looking at something that's too simple, it makes no sense. And I think that something like this is actually going on in biology, where the culture is actually probably primarily driven by theoretical physics. The kind of the ethos of theoretical physics of having an elegant, simple, universal theory that could explain a lot of this is what I think is happening in biology quite a bit. I think it needs a bit more of this type of an attitude, which says that we're going to deal with complexity head-on, and we want to be able to build sufficiently complex models so that we understand what is the real problem that the brain is trying to solve when it has to deal with these 100 billion neurons and things of that sort. Okay, I'd like to stop there. Thank you very much. Thank some of the people who supported this work, and I'll take questions if you are.
So if you back up to your last data graphs.
So which one?
The last set of graphs, your reprogramming.
Okay.
So if I understand correctly, you're measuring the inputs to the biomechanical system, the muscles. You're doing the simulation. And I can understand that, especially using your apparatus, you could run your simulation, you get a virtual 3D model of what the hand does. You actually look at what the real hand does. They're occupying almost exactly the same space at the same time. Your model's validated.
Right.
What's the validation when you do the virtual surgery? Because there's no ground truth there. And isn't it an extrapolation to assume that it works?
Yeah, there is a little bit of an extrapolation. Ideally you want to also, I think if I understood your question correctly, there's other kind of cues like your hand is actually moving in one particular way, etc.
But the analogy I would give is to neural nets, where you do this tenfold validation stuff. The idea is you're swapping in and out things so that all your training isn't on the real data. And aren't you kind of forced to be doing the training only on because you can't physically deactivate some of my muscles, for example.
Right, but maybe you're asking a different question, which is an easier one. So you can, but it is literally as if I mapped your muscles I'm only changing the effect, the mapping from your muscle to the motion of this object. Okay? So it's not unlike the mapping that you do when you have a new interface and you're moving it around from here. Suddenly you're moving your arm here and the object is moving there, except it's more complicated. Right? So you do have the feedback that your arm is moving here, but the visual signal kind of dominates, and you're trying to learn how to move the object on the screen. So I'm not sure I understand the...
Well, no, I understand what you're basically doing is feedback learning. So yes, but that's a new computer interface.
Right.
The question was, how do you know that if you actually were to do the surgery, the learning experience
I see what you mean.
So even the control function, therefore the learning experience is based on, would be correct.
So the answer is I don't. In fact, many of these surgeries you can't even do, right? Physically do, because you cannot just rotate. I could perhaps put a little sensor on each muscle and then drive a robot to me, but I can't just rotate all the muscles in space. So, but that's not actually the point. The point is mainly that it is it's a remapping that if you are, because these are, by the way, like you're asked to reach relatively quickly, etc. So if you are not suddenly starting from scratch and solving, okay, I have these actuators, what's my optimal movement, etc. But if you are using a set of modules, then it should have these types of effects. But we can't validate it unless you want to volunteer on how this actually would feel. Question.
Are there any injuries, muscular injuries, that you could use for people who already have defects in their muscles to check your models?
Yeah, that's a very good question. A related motivation is all this type of injuries like spinal cord injury and stroke. The main problem is it's a bit early to try to do that because it is still very hard to diagnose exactly what has happened when you have a spinal cord injury. It isn't like, okay, I know that this particular muscle has become deactivated, but that is generally the same kind of point. So you could simulate, for example, you could simulate a spinal cord injury in this setup and say that, okay, suddenly, this muscle has become weak or some such thing. But we were, so in the general setup, we could do a lot of those things. We were just trying to go after a particular question. Are these modules something that are actually represented in your brain?
I guess what I meant is like for people who already have spinal cord, I guess like
there's spinal cord injury and stroke is even worse because they're like they're large. There's a lot of generalized damage that happens. So if we had an individual that we know he or she has this particular deficit clearly, then that might be. Yeah. Good question.
I just wanted to ask a question about abstraction. And so, so you can build these great layered models with complexity at each and every layer from the bottom up. So it's a bit like the connectome, where you just scan the hell out of everything and you just build it in all its gory detail and apply it to the musculoskeletal model. And I totally believe that you can do that and all the rest. And so I guess the question I have relates to what do you then do with all that data, and how do you do parameter fitting to it, because each time you introduce another layer into the architecture and you point out, oh well, this is critical. If you don't model this, then at least in particular situations.
Yeah, I hear you. No, I think I know.
And so it's the parameter fitting.
So and I completely agree with you. And in a way there is an art to modeling in the sense that you don't just increase the number of degrees of freedom. Just like it doesn't just help to have okay, now next year we have a trillion megapixel camera because it's better than a 7 megapixel camera. It just depends on whether you want that, all that information. So a related question that I get on the other side is, why are you using these strand models? Why don't you just use finite element models with all of these types of, with a full distribution of materials? And that is related to exactly the same thing, because for muscles, especially for muscles used in motor control, we think that the mechanics along the muscle strand is the most important one, and we can ignore the mechanics of muscle in the other direction. If you were to come to me and say, in fact, several people come to me and say, can we use your model to do surgery? I want to kind of remove some tissue from the muscle. So this wouldn't be a good model for that. You would use a 3D solid model. Right? So part of you don't want complexity for the sake of complexity. You want complexity because you can represent things like these networks that you have. It's obvious that if you didn't have that network, you're missing something big. So there is a bit of an art to picking the complexity just right, and not just saying, okay, we've got big computers and we are going to get a high performance computing grant to use Westgrid to simulate some large thing, and let's just do it. Yeah.
So you talk about, like, what I understood as 3 parts. The first part is let's fly by flying the jet engine, and that's the graphics part. The second part, you start looking at the fibers and actually the fine modeling. And the last part actually is looking at, let's forget the physics of it, but let's actually look at the computational models that would have to be in place for these systems to take place. And like I echo Michael's view that you can understand how each neuron connects to the other neurons and still not be able to control the system or understand it.
Yeah. So you're absolutely right. I mean, again, to repeat a bit, I'm not suggesting, I hope you didn't get that impression that we take our single sarcomere model and then build a whole human model made out of a trillion, gazillion sarcomeres, and we're going to simulate the muscle. That's not at all what I'm suggesting.
No,
so what I'm suggesting is there is actually a phenomenon that if you ignore, which essentially everybody ignores, this kind of force enhancement issue, you make prediction errors of about 50%. Okay, so that is, if you don't take this into account, you're making errors of about 50%. So what I'd like to do is to connect the loop we haven't yet done, is to take these sarcomere models and then build a macroscopic model which you can then fit to data. But ignoring this phenomenon, which is causing very large errors, is not the solution either. So yes, there is an art, and I didn't mean to suggest that we're just going to build huge gazillion models. And,
So no, I completely agree. My question was coming at how far are we in understanding the third part of your talk? I mean, we
very far.
We have very basic motor primitives.
Yeah, very far. So I think no. I mean, it's insane. It's going to keep everybody busy for a long time, because essentially it's trying to. This is just, first of all, this one part.
Far from the goal or far from the start?
Far away.
We are very far away. We are very far away from the goal. So we are. This is, in some sense, we would have been closer if we had a negative result, because then we would, at least we could start from scratch. But at least it looks like there is some kind of modularity. But there are amazing. It's just. It is biology is just complex. It wasn't built for us to understand it. So we just have to try our best, keep going. Anything else?
Okay,
Thanks.